This is lesson 4.1, inverse functions, college algebra, page number 348. So a brand new chapter here. So the first thing that we're going to talk about, a lot of this is theory in this beginning, so this first video will be mostly just me talking with a little bit of drawing. But we're talking about inverses. And what it says here in the book, when we go from an output of a function back to its input or inputs, we get an inverse relation. So, for example, if I have some points on a graph, and I have 5, -8, and -2, 4, and 1, -7, and 6, they have 0.2, 3.8. Doesn't really matter, you just pick any points. The inverse of those would be going in the opposite direction. It undoes the function. So if we were to take this ordered pair and interchange the first and second coordinates, we would get an inverse relation. So all we have to do is turn these all around like this, and etc., etc. Keep going with that. So what happens is if we graph this first part right here, we get 5, -8, let's just stick a point, I'm not going to do all the counting, -2, 4, 1, -7, and we just go through there and make our graph. What we're going to do is, if you were to reflect each one of these points across the y equals x, you would get the inverse. So if we put, for example, 5 -8 here, when we change to -8, 5, it's going to go over 8 up 5, and we're going to get the inverse. So it's going to be the inverse. So jump right across, reflect right across the y equals x. If we put in there, like we have -2, 4, and then we do 4, -2, it's going to go over 4 down 2. It is going to be a reflection across the x-axis there. Okay, so that's what an inverse does, and all you have to do is switch the ordered pairs around and you get the inverse relation. So that is pretty easy to do. In the bottom of page 348 it says, if a relation defined by an equation, interchanging the variables produces an equation of the inverse relation. And so that's what we're going to look at right now, is what happens when we take an equation and actually interchange the variables. So for example, on example 2, they give us y equals x squared minus 5x. Alright, so the inverse relation would be x equals y squared minus 5y. Okay? So all we did was interchange those. So the graphs of a relation and its inverse are always reflections of each other across the line y equals x. And the y equals x is always a 45-degree angle going through the origin, just like that. So this and this are inverses, which means their graphs are going to be reflected, or the inverse is going to be reflected across the y equals x line. So for example, in the middle of page 349, it gives us the graph of y equals x squared minus 5x. That's going to look like something like this. And then its reflection across this red x or y equals x axis is going to look like this. Okay, so it reflects across the y equals x axis and gives us that. Okay, so not too hard to find an equation for the inverse of the relation. So should not be any problem doing that. So the next thing I want to talk about is inverses and one-to-one functions. Okay, so let's look at this top picture here. This is a table of a function. Notice that what we put in, our domain, our x value, what we're putting into the function machine, is spitting out only one option here. So in 1992, 29. 1994, 29. Even though they both point to the same number, 94 only has one line from it. Okay? Same with every one of these years here. They only go to one line. If 2002 went to 33 as well as 37, then it would not be a function because you've got two answers there. But in this one, in this graph, we only have one place that our x value is pointing to. So this top one here is a function. But notice when I flip them around, when I take the inverse. So here I've got 1992 going to 29, and here I'm taking 29 and going back to 1992. So remember what I said earlier, an inverse undoes or undoes another function. So we just turn our arrow around, point the other way. But notice when we go from 29, it points back this way. And it points to two places. And you're not allowed to do that with a function. So, going inverse, we're talking about it not being a function. And when two or more inputs of a function have the same output, an inverse relation cannot be a function. So see, I've got two or more inputs given me the same output, which means this one is a function. But if I just look at this, I know that if I do the opposite and I go from here back to this, like we did here, it will not be a function. So I can just look at this and say, okay, well this is fine. I've got a 1992 pointing here, 1994 pointing here. So both are pointing to 29. Both of these are pointing to 32. That's a function. But I can also look at this without seeing this table and say, but if I go the opposite, it's not going to be a function. Okay, and that's important because if the inverse is not a function, then it cannot be called what is going to be termed in this section is a one-to-one function. Okay? So it has to be a function this way, and it has to be a function this way in order to be what is called a one-to-one function. So one of the things that we're talking about here is we're going to give a new symbol when it comes to the inverse of a function. Right now, what you're calling a function is f of x. But what we're going to do to talk about the inverse of a function is we're going to put a -1 up there. That -1 is not an exponent, and it does not mean 1 over f of x. Okay, like we've done in the past. When you have a negative exponent, that means everything goes in its opposite position. But whenever it's together with an f of x, it means the inverse of the function. It does not mean the reciprocal. Okay, so just so you know that's how it works. Okay, so this is top of page 351, the properties of one-to-one functions and inverses. Now this gets to be a little bit tricky. It stretches your brain a little bit. But if a function f is one-to-one, then its inverse, f of -1, is a function. Okay? So if the function, like that picture we had before, and we showed that it was one-to-one, that if we went back and forth, and they were both functions, then we have the function and we have the inverse that is also a function. Another thing about one-to-one functions, the domain of a one-to-one function is the range of the inverse. So remember, the domain is the x and the range is the y. So if the x values of a one-to-one function, they will also be the range of the inverse, the y values. So if we have numbers between 1 and 10 in the domain, and the function is 1 to 1, the range will also include those numbers 1 to 10. The range of a 1 to 1 function is the domain of the inverse, so basically same thing, only backwards. And a function that is increasing over its domain or is decreasing over its domain is 1 to 1. So as we, and I'll just draw right here in the middle, as we have the domain getting bigger and bigger and the y is increasing here, up, 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 we have a 1 to 1 function. Or, on the other hand, if it's decreasing as its domain is getting bigger and bigger and bigger, it's going to give me that 1 to 1 function. Alright, so let's get rid of all this and start looking at some of the examples here. Alright, so given the function f of x equals 2x minus 3. It says prove that f is 1 to 1. Okay, one of the things that's true if we have a 1 to 1 function is if f of a equals f of b, then a equals b. So what that means is if we take and put f of a, we say that that's 2a minus 3, so I'm just taking it from here, and if I take f of b, and that's 2b minus 3, okay, and I said if they're equal, then this is equal, then they're 1 to 1. So let's make these equal. 2a minus 3 equals 2b minus 3. And let's just do the algebra. Those will cancel. And we get 2a equals 2b. Divide by 2, divide by 2. And we end up getting a equals b. So that worked. We got a equals b from that. So therefore, it's 1 to 1. If when we solve this we got a does not equal b, if we got something like 2a equals b over 4, then a and b are not equal. So then it would not be 1 to 1. But if we can take our function that they gave us, clear up here, and we plug in an a, plug in a b, and like we did over here, and we solve it and we get a equals b, then we know it's a 1 to 1 function. And this shows 1 to 1 functions, bottom of page 350, where it says a function is 1 to 1 if different inputs have different outputs. Or a function f is 1 to 1 if when the outputs are the same, the inputs are the same. So what I did is I took my outputs, my functions, my f of x, and I made my two functions equal to each other, my outputs equal to each other. Therefore, my inputs, my a and b, had to be the same in order for my outputs to be the same. Okay? So, that is just a real confusing section, and I'm not really all fired up that you understand all of this exactly, but if you just can kind of follow with what I'm saying, you should be fine, because when we get into some actual problems, the theory there won't be all out necessary to get. It is important to at least listen to, but it's not going to be a death sentence if you don't get it completely.